in this lecture, we will discuss partial molar quantities. So, we consider a simple non-reactive binary mixtures. So, we consider a binary mixture simple binary mixture we will consider. Okay. So, of two liquids, suppose A and B, and A and B they are non-electrolytes usually, we consider non-electrolytes. So, in our system there is no ions. Okay, so, we can write Na or Xa mole fraction of A plus mole fraction of B equals to 1. Okay. So, to understand the concept of partial molar quantities, the easiest property one can visualize is volume, right. Okay. The easiest property to visualize for partial molar quantities the easiest property to visualize is volume. Volume V. So, if we mix liquid A and liquid B, we can or we will have three different possibilities. Okay. So if we mix A and B, we will have three possibilities. Right. What are those possibilities? Possibility 1 is no volume change, or suppose we are mixing 10 ml of A and 10 ml of B, and if the total volume is 20 ml, then effectively there is no volume change in that sense that we are getting the expected volume. So, we get no total volume change. Okay, then we can have also volume contraction. And the third possibility is volume dilation. So, these are the three possibilities one can have. So, in the first case, suppose as I discussed, in the first case means there is no volume change. If we mix 10 ml of A and 10 ml of substance or liquid B, and if we get a total volume of ml, then we can say that there is no effective volume change. Okay. And in that case, the interaction or the AB interaction between A and B are equal to AA interaction, AA and BB interactions. But unfortunately, that is not going to happen for all the cases. Okay. But this does not happen always, right, as I said. Okay. So, you get either volume contraction or you get volume dilation. Okay. For example, the molar volume of water is 18 centimeter to the 3. We know it, we know that, right, that the molar volume of water is 18 centimeter to the 3, and the molar volume of ethanol is 58 centimeter to the 3. Okay. Now, if we add, so if we add 1 mole of water in large volume of ethanol, then what we expect? We expect the volume should increase by 18 centimeter to the 3, but what we get, if we add 1 mole of water in large volume of ethanol, we get an increase in volume of 14 centimeter to the 3, right. So, it says that the partial molar volume of water for that composition mixture is 14 centimeter to the 3. So, now we will discuss partial molar volumes. Remember, partial molar volume depends on composition. If composition changes, molecular environment will change and partial molar volume will also change. Okay. So, the partial molar volume, as I said, the partial molar volume changes with composition. Because molecular environment also changes. Okay. Okay. So, the partial molar volume is defined by, so the partial molar volume can be defined volume of a substance is defined by Vi, right, Vi is del V by del Ni at constant pressure, temperature and keeping the composition of other number of moles of other component fixed. Okay. So, once we know the partial molar volume of both the components, in the mixture, we can calculate the total volume, right? We can calculate total volume. Like V is Na times Va plus Nb times Vb. Okay, so Na is the number of moles of component A or liquid A, and Nb is the number of moles of liquid B. Okay. Now, how we can calculate partial molar volume, rather we see it. Okay, so we have V is Na times Va plus Nb times Vb, right? And Na plus Nb is the total number of moles, and if we say it is N, then you can write V by Na so you can write Vm is Xa times Va plus Xb times Vb. Okay. So, where Xa and Xb are the mole fractions of component A and component B respectively, and Vm is the molar volume, total molar volume. So, Vm is the total molar volume and Xa is the mole fraction of component A, mole fraction of A, and Xb is mole fraction of B. Okay. Now, if we differentiate, we get, on differentiating, we get dVm. Okay. On differentiating, we get dVm is okay, and then we can write dVm by dxb is Vb minus Va, and then we can write Vb is Va plus dVm by dxb. Okay. Now, if we substitute this Vb, then we get Vm is Xa times Va plus Xb we get this. Okay, so Vm is Xa times Va plus Xb times Va plus dVm by dxb. Okay, and then we can simply modify, and then we get Vm is Xa times Va plus Va times 1 minus Xa, okay, plus Xb times dVm by dxb. Okay, so Xb we can write, this is because as Xb is nothing but 1 minus Xa, right, because we consider binary mixture. Okay. So, what we get? So, finally, we obtain Vm is Va plus Xb dVm by dxb. Okay. So, we get finally this equation. Okay. So, now if we plot okay, so molar volume Vm versus mole fraction of component B, mole fraction of B or Xb, x goes from 0 to 1. Okay. So, when Xb is, so you get some kind of this type of plot you can expect. Okay, suppose you are getting this kind of plot. So, okay, so you get okay, so this is the molar volume. Okay, and then basically you can draw okay, so you get this is Vm of component A and this is Vm component B. Okay. So, for this value Xp you can get like this. Okay. Then we calculate partial molar Gibbs function. Okay, so we know mu I is del G by del Ni at constant pressure, temperature, and when Ni is not equal to Nj. Okay, and we have used here okay binary mixture of A and B. So total Gibbs function of the mixture, the total Gibbs function of the mixture we can write G is number of moles times of A times mu A plus number of moles of component B times mu B, right. Okay. So, if we differentiate, on differentiating we get dG is Na times d mu A plus mu A times dNA plus NB times d mu B plus mu B times dNB, right? Okay. And if you go back and check, we already obtained dg, we know dg is nothing but mu A times dNA plus mu B times dNB. Okay. Now, since g is a state function, so we can write, so since g is a state function, we can write Na times d mu A plus Nb times d mu B equals to 0. Okay, or in general you can write sum over I Ni d mu y is 0. Okay, and this is known as Gibbs-Duhem equation. Okay. Okay. So, next we consider chemical potential of liquids. Okay. So, next we consider chemical potential of liquids. Okay. For a pure liquid, in equilibrium with vapor, we can write mu A star liquid okay. So, for a pure liquid, suppose we have liquid A pure, then we can write mu A liquid equals to mu A naught plus RT ln PA. Okay. And for solution, we can write mu A liquid is nothing but mu naught A plus RT ln PA. And if we combine these two equations, so combining these two equations, we can write mu A liquid RT mu star L plus RT ln PA by P A star. Okay, so what is, so this ratio, the ratio PA by PA star is nothing but mole fraction of component A. Okay. Or we can write PA is XA times PA star, and this is known as Raoult's law. We have already studied Raoult's law. Okay. So, it follows that the chemical potential, thus the chemical potential of liquid you can write mu A L is mu A star L plus RT ln XA. Okay. So, this equation or this important equation is the definition of ideal solutions. Okay. So, alternatively we can say that an ideal solution is the one in which all the components obey the Raoult's law. Right? You already studied this thing. So, if we plot mole fraction of A versus pressure, okay. So, we can get a plot like this. So, when Xa is 0, this is nothing but Pb star, right, and when x equals to 1, this point x equals to 1, this is nothing but Pa star. Now, if we join these two lines, this represents partial pressure of component A. So, this is nothing but partial pressure of component A, and if we join these two points, okay. So, it is not drawn in proper manner, but you get a straight line kind of thing here. So, this is partial, this represents partial pressure of B. Okay. And total pressure is this one. This is nothing but total pressure P is Pa plus Pb. Okay. So, how total pressure is changing as we change the composition of the mixture. Okay. In ideal solutions, the solute as well as the solvent obeys obeys Raoult's law. But in some cases, in ideal solution, the partial pressure of solute is proportional to the mole fraction, but the constant of proportionality is not the pure component vapor pressure. But a constant known as Henry's constant. You already studied that, Henry's constant, Kh, or you can write Kb also if you want, okay. Kb, okay, write it Kb. So, Pb is Kb times Xp, okay. And this is known as Henry's law. This is known as Henry's law. Okay. Next, we consider, okay, next we can also plot actually, we can plot Henry's law. Okay. So, if we plot Henry's law, so we are changing mole fraction of B here, and this is pressure P. Okay. And then we can draw like this. Okay. This is nothing. When Xb equals to 1, the pressure is nothing but Henry's constant Kb, okay. And you get like this one. So, this is ideal dilute solution, this is for ideal dilute solution, okay. And you get like this, okay. So, this is how we can plot Henry's law here. Anyway, next we discussed, okay, excess functions. Okay, so in real solutions means the solutions that do not obey Raoult's law. Okay, so for Raoult's, so real solutions have different molecular interactions between A, AB and BB particles, right? Particles. As a result, we get delta H is not 0, delta V not 0. Okay. Suppose delta H is positive. Okay, and delta S is negative. Okay. In that case, since delta G is delta H minus T delta S, so we get delta G is positive. Okay. So, the liquids are immiscible. Right. The thermodynamic properties of real solutions can be expressed in terms of excess functions. Okay, so the thermodynamic properties of real solutions are generally expressed in terms of excess functions. Okay. For example, for entropy change, you can write excess entropy is delta S mix real, okay, minus delta S mix ideal. So, we get, now if we substitute delta X mix ideal by the expression we already derived. So, delta is, so SE or excess entropy is nothing but delta S mix real plus ANR XA ln XA plus XB ln XB. Okay. So, we in this context we can, in this context or in this regard, the concept of regular solutions is very important. Okay. In these solutions, HE is not equal to 0, but SE is 0. Okay. So, for the concept of regular solution is very important. Okay. And for these solutions, excess enthalpy is not equals to 0, but excess entropy equals to 0. Okay, thank you.